So, welcome everybody to the day 4 of this industry readiness workshop on CFD. So, welcome Dr. Joseph Prabhu.
Yeah,
Yeah, thanks. So, thanks for joining. So, we will begin with a small introduction of Dr. Joseph, and then we can start with the session. So, Dr. Joseph is a CFD engineer with a PhD from IIT Kharagpur, specializing in marine structures CFD. Currently, he is associated with the research division of Indian Register of Shipping. With over a decade of experience, Dr. Joseph Prabhu has a deep understanding of marine hydrodynamics. His research has led to development of numerical solvers, including a potential-based solver for maneuvering dynamics. This work has been recognized through publications in peer-reviewed journals and presentations at international conferences. Dr. Joseph actually also worked with us with the FOSSEE team on some part of the OpenFOAM GUI that we are developing. And that work has also been published and it is available for all at cfd.fossee.in. And Dr. Joseph Prabhu is proficient in both commercial and open source CFD software. He has extensive experience in solving a wide range of marine hydrodynamics problems using OpenFOAM. So like resistance and open water characteristics of propellers. So that was a brief introduction for Dr. Joseph. And so over to you, sir. We can start with the session.
Yeah, thank you, man, for a great introduction.
Thank you.
Okay, welcome all. So I was associated with FOSSEE team almost for last 2 years. So I have already submitted one research migration project with FOSSEE. So myself, Dr. Joseph Prabhu. So I am working in research and development division of Indian Register of Shipping. So we are located in Bombay near L&D Junction. So I'll just start with a brief introduction about my organization. And next I'll be discussing about what our organization mainly focuses on, and then my department, research and development, and what all are the activities we are doing in hydrodynamics group. Then this formation of IRS, it is formed in 1974 as a public limited company. It's the initiated by the Mudaliar Committee by the government during that time to support our marine industry in the for the development and research purposes. So it made as a public limited company as it should be collaborate with other countries and working. So it has no shareholders and it is financially and functionally independent. And it doesn't receive any grant from any source. It generates its own revenue. So we have some recognition from Indian administration. So we can assign load lines to our ships in both Indian and other vessels, other country flag vessels. Then we can carry out audit in ships and ports in accordance with international safety and international ship and port facility codes. And we can audit the ships based on whether it is sailing as per regulations, pollutions, norms, everything need to be checked. So we have 53 global offices, and outside India we have 26 offices, and in India we almost cover almost all the ports. And these are the departments. So here we have head of operations, so that they will be doing surveys at the ships. They will be boarding the ships and checking for the capabilities and other things. Then technology and innovation, they will develop some softwares that will be helpful for our surveyors. Then we have one training department, and we have rule development associated with research and external. So this department mainly focus on the development of rules, how much ship should maintain a particular speed and what will be the thickness for particular portions. That rules will be developed, and this will be followed by the surveyors during their inspections and all those things. Then research and development, where I am associated with. So here we have hydrodynamics and multiphysics, where I am working, and other we have marine and offshores and risk and reliability, then long-term strength. Then we have ships and technical services, classification, certification, and all those things. This classification, certification is the main part of our organization, as almost every ship should be classified by some of the society. Either in every countries almost have their own classification societies. So we will be representing India. So every 5 years they should go to our every ships need to be audited, and every 2.5 years it should be some intermediate survey need to be done to in order to sail it in the international waters. Then plan approvals center. So before building ships, the plan should be prepared by the clients, and that should be well approved with our organization, and then it will go to the yard, and yard will be constructing the ships, and that will be inspected periodically by our surveys. So from starting to till the delivery of the ships, our society will be getting them. So where our research and development, where we focus on these things. So ships have some, if in marine industry faces any problem, some ships due to regulations and some issues, some break, some updation, some ship may go to updation. And as per now, complaints is going on regarding the pollution and carbon reductions. So every strict regulation, they should be not carbon emission should be low as possible. So they need to reduce the improve the ship's efficiencies. So every ships need to be now carried out, improve the efficiency of this in order to maintain the speed to like that. So in the cranes, they approach us to maintain the check for how we can improve the efficiency of the ships. So we recommend some energy saving devices like propeller fin that we'll upcoming slides we will see. So in that way, we will be helping the marine industries. So these are the activities carried out in our hydrodynamics department. So this will be our daily jobs kind of things. So we need to be resistance computation is our basic job for all the vessels. So resistant computation we will be using commercial softwares, CCM, and occasionally we will be using foam also for this. So this template, we are resistant calculation templates we already submitted to FOSSEE. It is in research migration project. Those who are interested can go through it. It is multi-phase flow. So air and water and wave interaction will be there, and ship will be moving at particular velocity and how much is the drag. And we need to obtain the speed power curve. Then open outer efficiencies, that is for the computer, the propeller efficiencies. So they will remove the ship, we'll be keeping only the propeller and rotate the propeller at various operation and compute the thrust. This process is called open outer efficiencies. So this is to compute the efficiency of the propeller. So then next goes to the self-propulsions. So self-propulsion is the combined of resistance and open outer the things. We'll fit the propeller with the ship and rotate the propeller, and this propeller force is given to the body force of the hull, and that will be moving. From that, we can complete the efficiency of the ship. Then energy saving devices. So to improve the propulsion efficiency and the hull efficiency and other parameters, there are some energy saving devices like wake fins, propeller duct, and all those things that we'll discussing in later slides also more detail. Then other services we will be doing mooring analysis, some offshore rigs and any tugs need to be mooring analysis can be done. Then onboard noise. So if this is for normally naval vessels, any noise in the vessel due to the propeller engines, and propellers. Then evacuation analysis during in case of emergencies or fire or something, what is the evacuation procedure, and that analysis can be carried out. Then fire and smoke analysis. So if something got fired and the trajectory of the smoke and all those things. Then specialized analysis, we will be dealing with naval vessels. There we will doing underwater noise, radar cross sections. So RCS will call. This is for the normally naval vessels, it should be away from we need to hide out from the radar. So how much we can reduce our RCA signature. Then electromagnetic signatures. So that will be seen in detail. Then ship airwake. So ship airwake, this will be some naval vessels have halo operations. So aircrafts will be landing on the halos. So for that, we need to study the airflow along the halo decks and along the ship. Then underwater blast. So underwater blast means any blast happened at particular distance from the ship, how it will impact our ship. So we'll be seeing details of this. Then ship resistance is our keyword here. So this will be going as a multi-phase flow. So we'll be top air and below it will be water, and ship will be moved with a particular velocities. So using this, we can achieve the speed curve for various speeds. What is the resistance? So we will be having more benchmark studies like model test, and based on that, we will validate our CFD results. So there will be template approaches for that. We will having ITTC International Towing Tank Conference guidelines will be there. So that will be followed. And domain dimensions, how much domain we need to take forward after everything is given by ITTC. We can follow that easily, ready-madely. Now open water efficiencies, like already I talked about some things. So how we'll be keeping behind the hull, remove the hull from the ship, and just only rotate the propeller. This will be single phase, only water. It will fully submerged, and we will be rotating the propeller, and we can compute the thrust, torque, and the efficiency of the propeller. And this is self-propulsion. So this will be the combination of both the open water and the resistance part. So how much RPM is required to propel the ship at a particular velocities? So that will be, we have here the modeling will be a little bit critical. We need to make the propeller as a separate domain, that will be rotating domain. And there will be two methods, RBM and rigid body method. Rigid body method and moving reference frame, MRF and RBM. Okay. So in RBM, we physically rotate the propeller, and we will compute the forces on the transfer that force to the hull, and ship keeps on moving to overcome the drag of the ship. And MRF, moving reference frame, we will keep the propellers static and make the flow around that fluid particles to rotate in that domain. So that will be two techniques. So MRF approach will be with quicker results and computationally less expensive. But this RBM techniques will be time consuming and computationally more expensive. So for simple cases and where geometry complexity is less, we'll be going with RBM, and we will be in where accuracy and RBM is more accurate, and where accuracy doesn't matter, we'll go with MRF. So these are some energy saving devices. We can improve our propulsion efficiencies and the hull efficiencies. So first one is the wake equalizing, that will be placed below in front of the propeller. Okay, so video is not playing. So it will be, propeller will perform better when we get a proper flow. So some wake equalizer duct can be kept that will regularize the flow to the propeller, such that propeller can work more efficiently. Then we can keep some duct around the propeller. Then we can make in the hub, we can keep some PBCF fins attached with the hubs. That maybe also we can improve the propulsion efficiencies. So currently what is going on in the industry means that strict norms are there to ships, to that carbon emission should be minimum. It should not exceed to a particular limit. So in order to the old ships that we are built 10 years, 20 years back, normally the ship lives are tend to be 25 years. So older ships, both older than 10 years, are need to be compliant with this criteria. So what they are doing, so if the ship is normally moving at 10 knots, so they will be having a check on this carbon emissions. So, and based on the tonnage, it should be limited. So if it is emitting more, they should either you reduce the speed or reduce the tonnage of the ship. That will be a loss to the ship owners. So in order to further improving their old vessels, we will be fitting this kind of energy saving devices. So we cannot directly fit to the things. So for that, we will be using CFD analysis. So they will give the hull to us and presenting what is the propeller available with them, and we will be trying various energy saving devices, and we'll optimize, and the design goes to the yard, and they will manufacture and fit it, and it will be incorporated in the ship, and such that they can maintain the ship ship speed and tonnage, that without any loss they can run the ship. That is the purpose of this energy saving devices in current scenario. Then we will be doing some sea keeping study of planing hulls. So anybody having any doubts, you can stop me at any time. Okay, we can clear then and there, and we can move on. Okay, anyone having any doubts or clarifications? Then seakeeping study of planing hulls. So these are the seakeeping analysis. We keep move the hull at particular speed on particular waves. So these ROs of the ship motion. So whether this is based on passenger comfort, we will see we will be moving the ship and how much is the maximum vertical acceleration, horizontal acceleration coming on the ship. So for what speed we can go and what waves we can travel, that can be calculating during this. Then these are the mooring analysis. These we do in Moses to compute the floating platforms, how it should be moored, and when some ships need to be in static operations, for that mooring analysis can be, and tension in the mooring lines need to be checked using Moses. So then another thing, we already discussed a little about this radar cross sections. So this is normally applicable for the naval vessels. So we need to make the ship to be less exposure. So it's the measure of how detectable the ship is by a radar. RCS is the cross section produced by the reflected rays received by the radar plotted on the circular area. So we will be putting we will be regulating this in Alter FICO software. So we'll place them, pass them radar rays at all the 360 angles, and we'll find out the exposed area and which angle it is more exposed, we can computize. And our main aim was to reduce this RCS signature. It should be less. So we can make the body geometry less such that it will be reflective, or the radar ray should be absorbing. So higher this cross section area is the detectability of the ship. So for this process, we need to model the hull first, and we need to make a proper mesh, and we will be passing various RCS various frequencies like that range width, and we need to material properties also assigned to the hull bodies. So based on that, we can get the RCS signature around the hull for all the 360 degrees. So you can see at 90 degree and 180 degree, we are maximum exposed, and at 0 degree and 180 degree less exposed. So after computation, then how we can minimize this? So there are some equipments, some RAM equipments will be there. So we can fit it at wherever it is maximum exposed. We can observe this radar. So we can, in bottom graph, you can see the with equipment is the blue line is peaking out 60 degree in the range, and that can be when after fitting this equipment we can minimize it to almost 0. Then hotspot identification. So which part of the ship contribute to the highest mean of the RCS? based on the geometry, it will be giving the hot spots. So we can work on that particular area and reduce the RCS. So how we can minimize this RCS effect? We can target by shaping. The shape should be maintained such that it will be it should not be reflected back. And deployment of screens, application of radar absorbent material, that is called as RAM. Active passive cancellation techniques will be there. Then surface treatments. So these are these for 1 gigahertz graph, we can see the for 0 to 360 what is the RCS around the hull. So after fitting that radar absorbent materials RAM, you can say there is a reduce in the RCS effect in the hull. The static magnetic signature. This is actually whenever a ship or big mass of and metals are crossing the ocean, that will disturb the Earth's magnetic signature, and that will be sensed by the mines underneath, hidden by the enemies. So that will be triggered based on this disturbance of the magnetic fields. So sea mines are the major threat to the vessel operating in littoral waters, and electromagnetic signatures which governs susceptibility to sea mines is predicted based on electronic conductivity and magnetic properties of the hull. So effect of equipment, weight, vessel motion can be accommodated in the advanced studies. So currently we are not doing that weight and all those as activities cannot computed in our present software. So this can be minimized by placing, you can see that will be in upcoming slides, I think so. So numerical modeling of this thing. So first we need to model the hull and where propulsion plant, everything need to be detailedly modeled. And then we can find out the electromagnetic flux. So you can see the as Z both in X, Y, and Z components, you can see the electromagnetic signature along the length of the hull. So you can see. So how we can avoid these things by making coils in lengthwise and in horizontal ways and in transverse ways. By keeping these coils and counteracting that electromagnetic signature, we can nullify this effect. So such that this signature will not identify the mines beneath that. Then that is by that we are completed with the RCS study, and now we have some specialized analysis for the naval vessels, that is airwake analysis. So here the flow will be only single phase. We'll consider only the portion above water. We will take it as a single phase, and only air we will be blowing it in the top and computing the airflow along the cross section of the ships. So first we will be having new model test. We will be doing model test in some of the facilities available in India, and we will validate it with our CFD. Then we will proceed further. The main proper motto of this study is we need to find out the safe halo operating limits. So at what will be the operating limits of the halos land? The aircrafts need to be landed in this halo region. So for that, what will be the safe operating limit that will be designed? Any short circuit of funnel. So there will be plume coming out of the funnel, and that should be smoothly pass away behind it, and that should not be entered into any of the engine intakes. That should be also monitored. So this is the wind tunnel modeling test. So first this is 1:50 model of our vessel. So this wind tunnel facility we will do it in IIT Kanpur. So there will be the model will be printed it in 3D printing. Then it will be assembled, and then it will be kept in the wind tunnel, and it will be the exercise. Then vessel velocity will measure at the swing PAV. Then the model will be rotated at various headings and compute the flow along the hull. So this will be the computational domain. So this will follow one L length forward of the ship and 2L behind, and along the sides we'll make 1.5 and top we'll make 1L. And domain, this is the domain dimensions. Then observation planes. So we will be having vertical planes, horizontal planes, and transverse planes as in the images. We'll along the halo is our focus of main focus. So we'll making few planes in that halo regions, both vertically and we'll be horizontally also will be keeping, and transverse ways also be keeping, and we'll be measuring all the three components UV, W of the velocities. Then for validation purpose, from internal we will be getting the contour plots at these planes, and that we will be pointing out, we will be keeping probes in the CFD things, and we will be check one by two how it is deviating from the experiment, and we will be trying various numerical models like K omega, SSK epsilon, like Spallout alarms, like that various things we will be trying, and we need to fine tune our model to match the wind tunnel. And then in wind tunnel we can't, will be very expensive way, so we can't do all the test in wind tunnel. So few tests we'll do internal and validate with the CFD and find out the fine tune our model for proper mesh count and proper turbulence model. Then we'll run for all the oblique angles of the headings. So validation procedure, we will be doing one-to-one validation. So this left side image you can see it is got from the wind tunnel. They will be taking some few after when the flow is normalized or smoothened. They will be averaging the frames of 300 and they will be getting this contour. This is the hollow portion of this. And in CFD, we will be getting this. CFD, this flow is leads to highly unsteady. So we will be finding, so some iterations it will be more, we won't get this match this, so we need to find out which to, then we will be checking that iteration and validating purpose we'll use that frame. This is U component and the stream lines are overlapped above it. Then flow separation zones need to be computed in the halo regions. This is important actually when helicopter is trying to land behind the things. So any flow is coming and any circulation happens in some reverse flow. It might be sometimes whenever you might have seen many accidents have happened while halos are trying to land. While landing, that is a very tedious process for the pilot to land properly on the halos. So this is main thing is that because of this circulations, if some circulations or some sucking flow is there, means it will be pulled out and it will be crashed in the hull. So to avoid that, this study is made to find out the at what zone it is circulating, and if it is severe, we need to avoid that conditions to land it. So this is the safe operating limit. So this need to be prepared. So ALH is one of the helicopter's name. So first we will compute that various planes. So Z equal to 1, like from the above, from Z equal to the halo level, from that 1 meter height, 2 meter height, like various levels, we will be computing the velocities. And wherever we'll check further, if the velocity is at headwind and the crosswind and tailwind. So three things need to be said. Headwind is wind is coming from forward, crosswind is 90-degree, tailwind is from behind. So we need to check this. If it is exceeding, every helicopter has its own capacity and limits. So we need to check further. If it is exceeding beyond that, we need to mark it with the red portion is the limit is exceeding. So this particular case need to be avoided. Then temperature at critical equipments. So some equipments placed at the in this ships may be very critical. Some sensors will be there, radars will be there, everything. So when our plume comes out of the funnels, that will be passing and heating up this area, and that sensors may be affected. They may not perform properly due to this. So we will be perform a plume analysis as plume is exiting from the funnel and it should be smoothly passing from the beginning. Due to some circumstances or some wind flow oblique angles, it will be pulled back and hit it in the mast. and that increase the risk of the damage of the sensors. So this need to be studied. This need to be studied for various flows and various oblique angles, and we need to plot like that and check the temperature. So every sensor's limitation need to be noted, and we need to be checked like this. Then the plume analysis, main focus of the plume analysis is to check whether the plumes are passing smoothly and exiting via the aft. But in this image, you can see there will be some circulation. If the block body is there, there is a low pressure zone. So flow will be coming and plumes will be coming moving to the forward. That is heating up our sensors, and there will be intakes also for the engine rooms. Engine need to intake air from air, and it will be exhaust to go in. Sometimes what will happen means this exhaust will be circulate and again it will goes to the intake. So that will reduce our engine performance, and it is bad for our engine operations. So that should re-entry need to be avoided at any cost. So for that, this is the purpose of this plume analysis. And another thing, this plume will be exposed at high temperatures. So it should be, as naval vessels need to be, signature should be kept low when operating at other enemy territory. So we need to keep the reduce the temperature. So temperature need to be monitored. So if you are operating at risky zones, we should not be caught by our enemy things. So our signature should be kept low. So that temperature should be monitored. If the temperature is higher, we need to use some other measures to keep it low. So for that purpose, we have seen in the below image, we are measuring the temperatures along the keeping the planes along the cross section, and we are measuring the temperatures. So we have some infrared signature studies also we'll be doing. So based on that engine room temperature and everything should be minimized. Then shear flow analysis. So these images will show that shear flow, when flow is coming, so beyond the bluff bodies there will be circulations of the things. So that will be necessity for keeping the major equipments like some anemometers will be there. So for performing some operations in the ship, we need to know the velocities and to be maintained like that. So for that we can important. So this first image is beyond the funnel, and this is beyond the mast, and this is in the halo deck. So how we can see the vortex is rolling around. So that will make the halo operations difficult. So like this, we need to do it for various angles and various speeds. So it will come with a matrix of the cases need to be run in CFD, like various heading. Every 10 degree will be 10 degree, normally 15 degree will be keeping rotating, 15 degree, 30 degree, 45 degree, like that oblique angles will be rotating. And we will be increasing the 2-3 variation of 10 knots, 20 knots, 50 knots, like that. Various speeds will be trying out and computing which case try to be avoided, and finally we need to list it out what are the cases we need to be avoided and for the operations. Then anemometer is the one thing, as I already discussed regarding this. Anemometer is measured to the velocities at velocity of the ship. The ship is moving at particular 10 meter. In this image you can see if it is moving at 10 meter per second, anemometer should be measure it as 10, but due to some obstacles forward or behind, it may fail it some cases. So we need to plot it like a polar plot. At R0 means ship is heading in 0 degree, wind is also coming. So this anemometer 1, and there will be various anemometers in the ship. So at what angles, if wind is heading at what angle, with anemometer reading we need to take. So various anemometers will be there, but if you see anemometer 1 is good at R15 to R30, 30 to R30. So whenever it is 30 degree variations, anemometer 1 will be good. But other headings, these are over predicting the velocity. So 10 meter per it will show 11, 12. And when the wind is coming from the aft, it will be only less. It will be 50%, only 5 meters instead of 10, it will show 10. So like this, we need to calibrate it. Then anemometer 2, if you see, it may be in some other locations. It may not be good at all the particular headings. Some headings it is giving good and some heading it is not giving good. So like that, we need to, will be various anemometers on the ships based on the operations. So thank you from my side. So anyone having any queries, I have time to take some questions.
So there's one question in the chat. They were asking, how did you model the movement of the ship?
So there we can do 2-3 ways are there. We can make it as a sliding mesh and we'll put it as the hull in one particular domain, and that will be moving. Sliding mesh we can do. Else in this purpose, normally for resistance we won't move the ship. For seakeeping maneuvering we will move the ship. In that, one mesh will be moving with the ship. You can see from this slide, the ship has a separate domain, that will be moving domain, that will be moved with the ship. So, and that will be moving into another domain, another computational domain. So this is for seakeeping. That sliding mesh technique we will be using. And for normal resistance and all those things, we won't move the ship. Ship will be as a fixed, it's a rigid body, and only the flow will be there. Is it true?
Yes, sir. Thank you, sir.
So currently in open form, we can do resistance and even open water we can do. And I am currently working on how to find the self propulsion and other things. And we works on Helix also. It's an open source tool. They have some GUI based open source tool, but if we want GUI, we need to pay for it. Script based we can use in Helix. And other things normally will for ready. Our works may be daily one on new variations will come. So for quick solutions, we'll be using CCM. So those who are students, you can get my anything. You have any questions or something, you can talk to Payal madam, and you can communicate me. You can work if any students are interested to do some projects with us, collaborate. I am ready to, and our organization is ready to welcome. It's near. We are located nearby. It will be easy for our commuting and other purpose. You can consider for a BTech 6 months projects or something. Any one of the projects we can develop in form that we already discussed with Fileman. So any students or anyone interested, we can have a paid internship also.
So there's one more question in the chat.
Okay, I can't do this. So what are the optimized location to place ESD? So normally fins will be there. That will be mid hull, from mid hull to till 70% of the hull. We can stabilizer fins will keep. That will make the flow steady. That is one of the thing. Then wake equalizing that will be forward of the propeller, and rudder boss cap fin will be there. So in front of the rudder there will be one cap fin. Behind that will be linked with the close to the not touched, but it will be take the flow from the propeller. So that boss cap fin. So based on that, how we will design means based on the current geometry of the hull. So current geometry of the hull goes to old vessels. So hull we can't do much modifications. So based on the hull, how the flow is coming to the propeller, so we can try. We try all the variations and we'll say which one will be better. So some ships may be basket fins may serve the purpose. Propeller basket fins will be there. That will be keeping behind the propeller, and some may keep them equalizer duct to regularize the flow. Like that we can try it in CFD, and we can find out which is the optimized way, which one we can keep. Yeah, we can the internship be done remotely? Yeah, you can do, but you can come to once or once a week or something. You can come once and take the problems. We can discuss further. If you are in IIT in Bombay, then it is close by. It's hardly 1 or 2 kilometers. You can come. It is not you need to full time. You need to stay here or like that. You can work from your.
Yeah, I think online also they can do the internship, right?
Yeah, we can do it. No issue.
Actually, for FOSSEE internships and fellowships, CFD professionals like Dr. Joseph actually guides the students also. So last time also, Dr. Joseph has floated a problem, but unfortunately we couldn't match that problem to the applied the students who were selected. So maybe this time, if some of them are applying for the next fellowship, we will be announcing around January 2026.
Okay, ma'am.
Then we can.
It will go as a internship or it will go as a project
Internship.
like internship.
Internship for 3 months.
3 months.
Because people, what they do is, if the problem is not possible to be finished within 3 months, then a preliminary kind of report can be submitted. At the end of 3 months, and then that work can be carried forward, and people actually take it forward to publish it in conference proceedings, in book chapters, journals. So it's up to the guide who is guiding the student and the intern who is actually taking up the project. Yeah.
Nice. So it's nice if any students willing, you can ready to, if they like our organization and if our organization likes them, we can observe them here also, no issue. Yes, true. So if there are no more questions, we can go ahead with that. Okay, fine. Okay. Okay, thank you. So thank you so much, sir. Thank you for joining. It was a very informative session. Okay, thank you, ma'am. Yeah, thanks for joining, sir. Yeah. Bye.